Well, it's natural to introduce a homogeneous kth-order linear recurrence relation with the formula. There are some inconsistencies in this expression that complicate a detailed analysis. First, note that some of the terms of the sequence are on the right and some are on the left, and some of the terms have an explicit coefficient and others do not. We could eliminate these inconsistencies if we express the recurrence relation as, with associated characteristic equation. By extension, the non-homogeneous kth-order linear recurrence relation can be identified with the recurrence relation, which looks very similar, so it seems we could use the same characteristic equation for both the homogeneous case and the non-homogeneous case. For example, let's consider this non-homogeneous recurrence relation. If we omit the 3n plus 5, the part that's making it non-homogeneous, we obtain, which is homogeneous and has characteristic equation. As before, if our forcing function isn't 0, we might be able to eliminate it by subtracting. So from 1, we can subtract the previous set and get, we can define a new forcing function as the difference between g of n and g of n minus 1, so this new recurrence relation will also have a characteristic equation. Now note that the homogeneous relation corresponds to the k plus first degree polynomial equation. Consider the new characteristic equation. Splitting our terms gives us, which we can factor as, giving us, where this polynomial corresponds to the polynomial in the characteristic equation for the homogeneous equation. And since the solutions are the same, we have the following result. The roots of the characteristic equation for the recurrence relation are the same as the roots of the characteristic equation for this recurrence relation. Moreover, the latter has an additional root of r equal to 1. And since there's no real difference between a recurrence relation written this way and a recurrence relation written in the normal way, this gives us a general method of solving non-homogeneous recurrence relations with polynomial forcing functions. For example, let's try to find a general solution for the recurrence relation. So our non-homogeneous recurrence relation, we'll put down our coefficients, prepend with a minus 1 and postpend with a 0, and find our differences. And so this becomes a new recurrence relation where f is some constant polynomial because we started with a linear polynomial. And again, we can set down our coefficients, prepend with a negative 1 and postpend with a 0, find our differences, and get another recurrence relation where we've gone from a constant term and eliminated it. And so now we have a homogeneous recurrence relation, which has a characteristic equation. Now, to solve this equation, we note that since it has the same roots as our original, the left-hand side has to have a factor of x squared minus x minus 2, and so we can factor it as, and we see that the roots of the characteristic equation are x equals 2, negative 1, and 1 with multiplicity 2, and so the general solution will be, since the additional roots are always 1, then in practice we don't actually need to find the homogeneous recurrence relation. This suggests a general procedure. Solve the homogeneous recurrence relation, determine the number of differences needed to form a homogeneous recurrence relation from the original, include that many additional roots of 1, then write the general solution, and if enough information is available, find the coefficients. For example, let's try to find a general solution for this recurrence relation. The homogeneous recurrence relation has roots of 2 and negative 1. Since the forcing function is linear, then the first differences reduce the forcing function to a constant, And the second difference eliminates the forcing function altogether. And so r equals 1 is a root of multiplicity 2, and so the general solution will be what if we added a quadratic term to our recurrence relation? We'd need to find the third difference, which would introduce r equals 1 as a root of multiplicity 3, so we'd add. In other words, we'd add a quadratic term to our recurrence formula. This suggests that, in general, to find a closed form for a non-homogeneous linear recurrence relation where our forcing function is a polynomial of degree r, we find a closed form for the homogeneous recurrence relation, and then modify our solution to Sn plus g of n, where g is also a polynomial of degree r. So let's find a closed form solution for the homogeneous recurrence relation, solving giving us roots of 3 and negative 2, and so we get our general solution. Since the forcing function is quadratic, we'll also add a quadratic polynomial. We have 5 unknowns, so we'll need 5 initial values, so we'll use the recurrence relation itself to find. We have initial conditions, and so this gives us a system of equations, which we solve and find. And so our solution is going to be